Thank you. Very nice to be back in Vienna, of course. Basically presenting the proof of this recent result. This is a result in the recently popular area called Generalized Baire spaces. So this is the theorem. Any kappa close forcing adding a dominating kappa real adds a Cohen kappa real. So a bit of background. Why is this interesting? In the classical case where we have reals as functions from omega to the omega, so the classical Baire space, we know that we can manipulate Cohen reals and dominating reals. So in particular, we know that Cohen forcing adds Cohen reals and not dominating reals, and we know that Laver forcing adds dominating reals and not Cohen reals. And in the language of cardinal invariants of the continuum, I guess I don't need to define these, but if you iterate Cohen forcing, you get a model where the covering of meager is large and the bounding number is small, and vice versa. If you iterate Laver forcing appropriately, you get a model where covering meager is small and the bounding number is large, and this is because the bounding number corresponds exactly to adding dominating reals. So to increase B, you add dominating reals. To not increase it, you don't add dominating reals. And similarly with covering of meager and Cohen reals. In the Chichon's diagram, this corresponds to that place in the diagram, B and covering of meager. So it's actually it's a quite important. It's the center of that diagram. It's quite an important thing, and in recent years there is this popular trend, let's say, to study generalized Baire spaces. So what we do is we try to translate all the results from the omega case to the kappa case, where kappa is an uncountable regular cardinal. So again, I'm not really going to go into details, but basically, if you do that, so kappa is a regular uncountable cardinal, you look at the space of functions from kappa to kappa, you use the topology, the so-called standard topology, where the basic open sets are all the extensions of a less than kappa sequence. And if you do that, you can generalize in a natural way these concepts: dominating real, Cohen real, the meager ideal, or kappa meager, union of lower dense sets. You can generalize kappa Cohen forcing in a natural way, and you can generalize the two cardinal invariants in a natural way, and you can basically look back at the program, and people have tried to generalize the classical results about these cardinal invariants to that kappa case and to see which cardinal inequalities hold, which independence results by forcing can be generalized and which cannot. And in particular, there are some problem with the null ideal. But with B and covering of meager, there's no problem, at least to define them. Okay, so so if we do that, then we can generalize Cohen forcing, and we can easily prove that kappa Cohen forcing dominating kappa reals, and therefore you can iterate it and obtain a model where the B kappa number is less than the covering of meager kappa. And the question that was asked in this paper, which is one of the papers dealing with the generalization of the Chichon diagram, whether the reverse is consistent. It seems like a fairly basic question. It's one of the basic things that you can ask in generalized cardinal invariants. Well, okay. How would you do that? As I said, the natural way to do that would be to iterate a forcing that adds generalized dominating reals but does not add generalized Cohen reals. Okay, there is this rumor that in fact the consistency has been proved by Schellach, but not with the method that I just mentioned, not by adding dominating reals which don't add Cohen reals, but doing it the other way around, by starting with a model where the continuum is large and the bounding number is large, and then adding a small witness to covering of meager. And why is this a rumor? Because as far as maybe somebody else knows more, but as far as I know, there is a reference in some note to a paper that is not accessible and where it claims that this has been proved, but I cannot find the actual proof. So in any case, I guess that this is correct, and I guess that sooner or later there will be a way to find. But what have we done? Right. So the result that I prove is still important, even though first I was hoping that maybe we would prove the. We would actually have a ZFC prove that B is less than covering of meager in the generalized case, which would be really nice. And this is apparently not the case, but it is still the case that any kappa clause forcing adding a dominating real as a Cohen real, which means that you cannot obtain this result, this consistency result, by iterating a kappa clause forcing. Okay? Sorry. Okay, so how is Laver forcing involved? Well, if this were possible, right? It's not possible. If this were possible, then a kind of Laver forcing would be the most natural thing, the most natural way to do this, and therefore we will prove a preliminary result first in detail. So first I will prove that any generalization of Laver forcing necessarily adds a Cohen real, which is, let's say, the first step to that result. It's not strictly necessary for the proof, but I think that the proof is much harder to understand without proving that first. So first we'll prove that any kind of generalization of Laver forcing as a Cohen real, and then we use that idea to get the main result. Right, so what is Laver forcing? In classical case, I guess most people know this, but it is a tree which has an initial segment, let's say it has a stem, and after that stem, it splits to omega many successors all the time, and so on. Right? And L is the forcing consisting of those trees ordered by inclusion, and we know that this forcing adds dominating reals and does not add Cohen reals, and even you can iterate it and it still will not add Cohen reals. So we try to generalize this. How do we generalize this? Well, in the most obvious way, we say that a kappa Laver tree is a tree in kappa to the less than kappa, which is, first of all, limit closed. This is a special condition that we want all forcings on kappa to have, right? So we want that if you have a tree, you don't have any dying out branches, basically. So if you have any increasing branch, then the limit of that is also still in the tree. And moreover, you want the same condition. So you want that there is a stem, and after that, it splits to kappa many. It splits kappa many to kappa many successors. Okay, this is just the most basic definition. In itself, if you use this as forcing, if you try to force with this, you can easily see that it doesn't work. It's not even sigma. It's not even sigma closed. It's not even omega distributive. But there have been attempts to define stronger versions of that. For example, where you say the splitting has to go in a club, so that you do have kappa closure. And you could, in theory, think of other ways to generalize by putting additional conditions on these trees. But the point is that it doesn't matter, because no matter what you do, no matter what kind of extra conditions you put, it will always still add a Cohen real. Okay? So this is our, let's say, first main result, that if P is any sub-collection of those things, so if it's any forcing whose conditions are these Laver trees, even if there's additional conditions on those trees, it doesn't matter, as long as it is closed under this very trivial condition, which says that given a tree and given some node in the tree, if you look at the cone of that tree below that node, you get something that is still in that forcing. As long as your forcing is closed under this very basic condition, you're going to add Cohen reals. And yes, and here is the proof. The proof is as follows. We consider this game, the Supremum game, where S is a stationary subset of the ordinals below kappa with finality omega, and player 1 plays unbounded subsets of kappa, and player 2 plays an element in it, right? So player 1 plays a kappa-sized subset of kappa, player 2 has to pick an element of it, then player 1 plays another one, player 2 has to pick another element in it, and so on and so on. And player 2 wins if the sequence she has produced converges, the supremum is in S, okay? In that stationary set. And the lemma says, if S is a stationary set, then player 1 does not have a winning strategy in this game. Right? So we're not saying that player 2 has a winning strategy in this game. And here's the proof. It's elementary model proof, which is not very hard. Right? So suppose player 1 did, right? Suppose player 1 had the winning strategy had the winning strategy sigma. You take a elementary, you let M be an elementary submodel of size less than kappa, containing the strategy, and such that the supremum of its kappa, which we call delta, lies in S. That's the most important step of the whole proof. And why can we do that? Well, we can do that because the collection of such deltas is club, and our set S was stationary, so we can find one model that has this property. Okay, then delta is that limit of the ordinals of M, and it has cofinality omega, so we fix a cofinal sequence which is a subset of M, not an element of M, and then we just proceed inductively at each step. 4 was in M, and the strategy is in M, and therefore the next step of player 1 is also in M. And by elementarity, we know that the ANs are unbounded, so H theta believes that it is unbounded, so H theta believes that there is something above gamma n, which is in that set. And so this is true by elementarity in M, so we can pick a beta n in M, which is above gamma n and in A of n, right? So if you look back at this game, it means that player 2 picks something in according to the rules of the game, and in such a way that this beta are above gamma n and that they are in M. Well, you do that, and then you obtain a sequence which converges exactly to delta because it's in M, so it converges to the, on one hand it is below delta, on the other hand it is above gamma, n, and therefore it converges exactly to delta, and therefore this was a winning condition for player 2, and thus player 1 did not win the game. Okay, so it's essentially it's a kind of standard argument involving elementary models. The only really important idea is that this exists, that such a model exists, with the supremum converging exactly to it. What does this mean? This means that if we define a short couple Laver tree to be just like this, but of length, of depth omega, so I'm now talking about omega and kappa, and a tree which is kappa splitting everywhere, right? So I call this a short Laver tree. Then from that game argument that we just had, it's going to follow that if S is a stationary subset of kappa omega of kappa, then there's going to be a branch through this tree that converges to S. So whenever you're given something like this, a short thing, then the game is going to give you X tree which converges to that stationary set. And that's because the game gives you exactly this. And what does that mean? That's essentially the whole idea. This means that you can define the function phi as follows: fix a stationary costationary partition S0, S1, and map, let phi be the map that takes a kappa real, that takes an element of kappa to the kappa, and basically chops it up into omega parts, right, into omega sections, and maps each one of those to 1 or to 0, depending on whether the supremum of that part is in S1 or in S0. Yes, is this a clear definition? So you take something of length kappa, you just chop it up like this, omega times 2. You look at each segment and you check whether the supremum of this is in S0 or in S1, and then you map it to 0 or 1. And the same with that part, you map that also to 0 or 1, and so on. That's just a very neat continuous function. And that's basically the proof, because now if you're given this collection of trees, if xg is the generic real that is added by that forcing, then the phi of that is going to be Cohen, just because, well, because you fix a Cohen dense set, you're given this tree, you have some stem here, you look at the image of that under phi, and you want to hit an arbitrary dense set. What does that mean? That means you need to go along some sequence of 0, 1, 0, 1, 0, 1, whatever you need in order to get into the dense set. Well, but you can always do that because of this game argument, and because we have a tree here which is limit closed, you can always continue, and you can always just say, well, I'm going to go like this. I'm going to go into S0 because I need to get a 0, then I'm going to go into S1 because I need a 1, then I'm going to go into S0 because I need a 0 again, and so on and so on and so on and so on. And you continue as long as you need until you reach exactly the condition that you need, and then you go there and you restrict your t to that point, and the image of the generic is a Cohen real. Very simple. Okay, and now let me give the sketch without details how this idea is used to prove the main theorem, because the main theorem does not talk about Laver trees in itself. It talks about an arbitrary kappa closed forcing. We need a little technical thing. The technical thing is a so-called strongly dominating real, right? So we were talking about dominating reals. That means that you compare two functions and you say whether one is higher than the other. But in fact, the more natural concept in technical terms is a so-called strongly dominating real, which is defined as follows. If you are given a function f from initial segments to kappa, you can think of it as a strategy or like a prediction function or something. And then we say that x strongly dominates f if eventually, right? If eventually x beta is larger than what x would have predicted it to be. You can say it this way. And if we have a model, then we say that x is strongly dominating over m if it strongly dominates every one of these predictions. And it's easy to see that if something is strongly dominating, then it's dominating. Vice versa is not true in general, but it is true that if we have a model with the same initial segments, right, with the same kappa to the less than kappa, then it is true that if there is a dominating real over m, then there is also a strongly dominating real over m. So for the purpose of adding a new real. It doesn't matter whether you talk about strongly dominating or dominating. And this makes a lot of stuff easier. You'll see in a moment. So yeah, so let now P be an arbitrary, and let X dot be a name for a real, and we define this U dot X to be the, let's say, the decision structure, right? So all the sigma and Q, where Q forces that sigma is an initial segment of X. And we put this ordering on it, right? We put this ordering, which basically means that tau R extends sigma Q if the initial segment is longer and the condition is stronger, right? So it's like you have stronger conditions that decide more and more and more of the real, and that is exactly that structure. Even though this thing in itself is not necessarily a tree, but it's still useful to think of it as a tree, so we'll still call a tuple like that kappa splitting if it is the case that there are kappa many successors in the first coordinate and corresponding kappa many extensions, direct extensions in the forcing, which will force that, right? And otherwise we say that something is less than kappa splitting. And the main point is that if X is a name for a strongly dominating real, so I don't know how this works with dominating reals, but for strongly dominating reals, if X is a name for a strongly dominating real and this is forced by P0, then for every P there exists a stronger Q and a sigma in that decision structure, such that, here's the main point, such that anything else in that decision structure that extends it is kappa splitting, right? So it says something almost like there exists a Laver tree in the projection of the decision structure. That's really the main point, and I'll skip the proof of this lemma. It's technical but not too hard. But basically, once you have that, you have the proof of the main theorem, right? Because now what happens is, suppose P adds a dominating real. Well, we also know that it then adds a strongly dominating real, and that's the one we're really interested in. So we let X dot be the name for that strongly dominating real, and we claim that phi of X dot is forced to be kappa Cohen, where phi is exactly the same function that we had here. And what we do is exactly what you would expect, namely we construct a kappa Laver tree in the projection of this decision structure, where, well, according to that lemma, there is this point after everything gets kappa splitting, so we use that to find extensions and inductively build this Laver tree, and whenever we reach limit nodes, we need to move on, we need to continue, but we have kappa closure, so we can continue by kappa closure of the forcing and find the continuation, and then we go on the same way. And then basically you construct this kappa Laver tree in the projection of the structure to the first coordinate. And then you do exactly the same thing as you did before. You use the Supremum game, you use this argument to go along this Laver tree, and you end up with a condition, you end up with a sigma in the tree and the corresponding Q, which forces that this is an initial segment of X dot, and sigma and the phi of sigma is precisely what we needed. All right, so precisely what we needed means whatever that Cohen dense set gives us, so some sequence of zeros or ones, we can find a initial segment of X dot where sigma goes exactly the way we need, so phi of sigma is exactly what we need, and then Q is going to force that what we need is an initial segment of phi of X dot, and therefore phi of X dot is Cohen real, is a Cohen real. That's basically the proof sketch. Okay, so the last thing I want to say is, sorry, can we improve this? In a sense, this is a very, I think it's a kind of complete result in the sense that being kappa closed is a very typical condition that we want when we do generalized Baire spaces, because that's exactly what you need to, not exactly, it's sufficient to prove that kappa to the less than kappa is not changed, that you do not add any shorter sequences shorter than kappa, right? But I guess it would, an even weaker and sufficient property would be less than kappa distributivity, so ideally we would like to even prove that every less than kappa distributive forcing has this property. If it has a dominating real, that's Cohen real. And we have some partial things. So the first comment is that we can actually improve this partition argument, the stationary partition and the function, and by using a slightly different argument, we can improve the result to every forcing which is kappa distributive and sigma closed. So you actually don't need kappa closure, you just need kappa distributivity, but you still need sigma closure. You can actually change sigma closure to strategically sigma closed, which is a slightly weaker property. And in a different direction, if we know that P is a tree forcing, and we know that the strongly dominating real is the image of the generic real by a Lipschitz continuous function in the ground model, then in fact kappa distributivity is enough. But in general, we don't know whether kappa distributivity of the forcing is enough. So for some time I thought the answer was yes, but it's not very clear. Yes, that's it. Thank you.